in our last class, we did this. We took the impulse response of a discrete time system. So if I input an impulse, I get the impulse response. Then we took any arbitrary signal, we decomposed it as many unit impulses, not unit because they are weighted by some values. So weighted shifted impulses, as represented here as well in the equation. Each of them yielded an impulse response, also shifted, also weighted, and then we summed all the shifted weighted impulse responses to get the output. And this was the discrete convolution. So the output is a sum of impulse responses because we decomposed the input as a sum of impulses. So now we're going to do something very similar to continuous time systems. Here, defining the unit impulse is a bit more complicated. Maybe we could try to define our unit impulse as a signal that is zero everywhere except for the time zero, and here it is 1. But this signal would have no energy, it would have no momentum, no area, it would input no energy to a system, so the output would be basically 0. So we have to define something different here for continuous time systems. Let's define this, a signal R of t, R for rectangle. So this signal, let's draw it here. It is parametric. We need to define a parameter delta. So if the absolute value of t is within delta divided by 2, so here is delta divided by 2 minus delta divided by 2, then the amplitude is 1 over delta. Elsewhere, it's 0. What is interesting about this signal is that it has unit area, so it provides unit energy, unit momentum to the system. So it is our best candidate now for the continuous unit impulse. So if I input this signal to a system, let's call the system output P of t. So P of t is kind of an impulse response. It's the response to our R of t. Here in this example, delta equals 0.5. So the non-zero part here starts at minus 0.25, goes up to plus 0.25, and the amplitude is 2 because it's 1 over 0.5. If I have this input, I have this output. The question now is, what is the output that I get when I put this, an arbitrary signal, at the input? Well, our best guess is to decompose this guy as a sum of R of t. It's an approximation, right? This is the actual x of t. The red one is the approximation, and here is the difference, the error of the approximation. It's quite large if I have delta equal to 0.5, but let's see what's happening here. So I am approximating x of t. Let me put a hat on the x to denote the approximation. I am approximating it as a sum of r's of t. So this one, for instance, it is r of t minus delta, because here the r of t is being multiplied by 0, so it's 0 if we get the first non-zero, it's this one. This guy is r of t minus delta, and it is, recall that the amplitude of r of t is, in this case, 2. So let's multiply by delta here. So this guy has unit amplitude. So if we multiply this guy by the value of x at time delta, then finally we get this value here. So this is unit amplitude, this is amplitude r x of delta. We can do this for the preceding one, the prior one as well. It's x of 0 times, let me put this more to the right, x of 0 times delta times r of t, which in this case, the x of 0 happens to be 0, but it's not always the case. So let's consider this guy here. So the next one is 1 delta to the right. So then 1 more delta to the right. I have the x of this guy here, amplitude, x of 2 delta, because here I have x of 0, x of delta, x of 2 delta is the amplitude, and it is multiplying an unit amplitude r of t. So I'm putting the delta to ensure the unit amplitude r of t minus 2 delta, and so on and so forth. And this concept of so on and so forth also applies here. So I can, my signal can have non-zero values from minus infinity to infinity. In this case, it's very short in time, but let's derive the equation for the general case. So our approximation x hat of t can be written like this: k from minus infinity to infinity, x of k delta, delta to ensure unit amplitude, r of t minus k delta. This is how we approximate any x of t as a composition of r's of t. Okay, and then each of these r of t will produce an output p of t, right? I input this, I get this, I input this, I get this, and so on. So we can write an approximation of what will be the output of the system for this x of t. We just substitute the r of t with p of t here. So p of t minus k delta. For each r in the input, I will have a p at the output. And the multipliers are just reproduced here. Okay. So a summation from minus infinity to infinity. And you might have noticed that this really looks like the discrete convolution, right? Here's the equation for the discrete convolution, because the principle is the same. We're just trying to discretize the problem here, because it's more familiar to us. We would know how to proceed. So there's an error here, right? You might expect that if I have the input for another r of t, but with a shorter duration, with a shorter delta, then my error would be smaller, both in the input and in the output. So that's what I have here. Now suppose I have the output of the system for this r of t, slightly shorter amplitude, 0.4, a slightly shorter duration, 0.4, slightly larger amplitude, 1 over 0.4. So this is the output. If I do the same here, I have a slightly smaller error, both here and here. And we can apply the same idea. If I have the output for this guy, surely my estimate of the output for x of t will be more accurate, and you might expect that I'm going in the direction of delta approaching 0. Notice that here I have many let's do here because it's easier to visualize. I have many rectangles with very short duration, but they're not very high in amplitude because I am multiplying by this delta. So I have many very low amplitude responses here, but they are so many that when I sum all of them, they sum up to something reasonably large in amplitude. So here I'm in a very advanced case where delta is 0.05, that is 10 times more accurate than my initial case, which was delta equal to 0.5. Question now is, what happens when delta tends to 0, when delta approaches 0? Well, when delta approaches 0, actually delta is a measure for a time step, right? When it approaches 0, let's call this step d tau. We could call it dt, but let's call it d tau because t is already being used here inside the equation. So let's use tau as an independent variable here. What else? The k times delta, k times delta is tau. This was an independent variable for time. Now it is a continuous variable for time. This guy was an infinitesimal step. It becomes here really infinitesimal. What else do we have? K delta, delta. Well, in this case, R of t will be a signal that we define it here. It will be the Dirac delta. This is how we represent it. So the Dirac delta is basically an R of t with duration approaching 0. Consequently, its amplitude approaches infinity, and this is why you represent the amplitude with a up pointing arrow like this. We have this axiomatic definition which avoids infinity. So we say that the value is 0, the value of the Dirac delta, our unit impulse is 0 for non-zero times, and the integral, the area of the signal, the total area is 1. So the only way to make this possible is that the signal tends to infinity here. So we put this arrow when it is an unit impulse, when the area sums up to 1, we place the arrow at amplitude 1, but we can have an impulse with magnitude 2, for instance, then we would put an arrow at amplitude 2. So this is our continuous unit impulse, just like we had discrete unit impulse here. We have now a continuous unit impulse. The definition is a bit more tricky, more complicated, because things infinite and infinitesimal in the continuous domain are a bit more complicated. So we defined our unit impulse, and this guy, the output that the system gives when I input an unit impulse is what we call the impulse response, the age of t. So r of t becomes the Dirac delta, and p of t, which is the response of the system to r of t, becomes the impulse response. Okay. So we can rewrite these two equations. We can define the input. It's no longer an approximation. Then I don't need to use the hat. We can define it as an integral minus infinity to infinity x of tau. This delta will become the d tau. I place it here, and this guy will be the Dirac delta of t minus tau. And now I have defined the input as a sum of Dirac deltas. And this will allow me to define the output as a sum of impulse responses, as a sum of responses to the Dirac delta. So I just reproduce the equation here, y of t, no hat because it's no longer an approximation, minus infinity to infinity, x of tau for amplitude, and where I have the impulse, I will have the impulse response, t minus tau d tau. Okay, and this is the convolution integral. This is the convolution of x and age. We can also represent it with an asterisk, like this. This denotes that I'm doing the convolution of the two signals. So now, just like we did with discrete signals, let's cast the problem, let's cast the integral and see the things happening here. So here my independent variable is tau, so I have x of tau, I have this age of t minus tau, I have to multiply them and then integrate the product, right? So let's draw x of tau here. The time is tau. It is more or less like this, going up to 3 with maximum amplitude 5. So what is age of t minus tau? I will take age, so age is here, this is age of t, so age of tau would be the same, would have the same shape. The age of minus tau is mirrored in time. It goes from 0 to, instead of 1, minus 1, and maximum amplitude 2. This is age of minus tau. Then if I want to have, for instance, age of 1 minus tau, I have to shift this guy 1 to the right. Then it would no longer be minus 1 to 0, it would be 0 to 1. X of 2 minus tau, 3, and so on. So I have the figures here. In this slide, in this case, I have the x of tau and age of minus tau. And here, 1 minus tau, 2 minus tau, 3 minus tau. So then we, for each case, we make the product of them both. It's here. And we integrate the product and get the value of the output for that t, that instant of time. So t here, it will it will cause a shift here inside the equation, right? So we can see that in this case, for negative t, there's no juxtaposition of these two signals, so the product is 0, the integral is 0. But then here for t greater than or equal to 0 until 2, what I have is the following case. I have something, the product, something that starts at 0 and ends at, what is this? This is t. Okay, so from 0 to t, I have to integrate this product from 0 to t. Here in this interval, since this guy is shorter than this one, I have an interval here where the limits are only defined by this guy. So it's from t minus 2 here, from t, so from t minus 2 to t. And then there is another case where the limits are t minus 2 to 3, which is the end of this signal here. So t minus 2 to 3. And then finally I have 0 of juxtaposition. So let's do this now for another signal, another pair of signals. And let's find an analytical expression for the output. So my input will be this, e to the 0.5t u of t, it's represented here. The impulse response is a 2-second moving average. So the impulse response has a duration of 2 seconds and has an amplitude of half, which is 1 over the duration, right? So it's the 2-second moving average. Let's see what we have here. And let's draw our y of t. Okay, so we can see that for t smaller than 0, y of t is just 0, right? Because I have nothing here in the product, so it's just from 0 on that I have something non-zero. So y of t is 0. So in this interval, let me choose another color here. In this interval, y of t is 0. Then for t larger than or equal to 0 until 2. This regime will last until 2. Until 2. What do I have? Let's check it. So here I have x of t. It's being, notice that it's being integrated from 0, because it starts at 0 here, so it's integrated from 0 up to t. This is t. Okay, and it's multiplied by half, and it's integrated from 0 to t. So for this interval, we have y of t equal to 0.5, the integral of from 0 to t of x of tau d tau. So 0.5, 0 to t, x of tau is e to the minus 0.5, here we put tau, u of tau d tau. So 0.5, we can neglect this guy because the integral is starting at 0, so 0 to t e to the minus 0.5 tau d tau 0.5. We have to pass this dividing here, minus 0.5, and then e to the minus 0.5 tau from 0 to t. So this guy is minus 1. And then we have e to the minus 0.5 t, e to the minus 0.5 t minus e to the minus 0.5 0. So e to the 0 is 1. That's what we got. So we just swap the signs because of this minus 1 here. So we got 1 minus e to the minus 0.5 t. This is the expression for this interval. So let's get back to this color. Until time 2, we have this curve, which is 1 minus e to minus 0.5 t. Okay? This lasts until time 2. Because from then on, there will be another expression, because the limits will be set completely by this rectangle here. So the limit of the integral will go from t minus 2 to t. Okay, this is t, so this is t minus 2. So let's do this again. So for t from 2 on, okay, y of t equals 0.5, the integral from t minus 2 to t of e to the minus 0.5 tau. I can neglect the u of tau, right? D tau, because I'm operating on an interval where this is always larger than 0, so I can neglect this guy. Again, 0.5 over minus 0.5, then e to the minus 0.5 tau from t minus 2 to t. Y of t is minus 1. This is e to the minus 0.5 t minus e to the minus 0.5 what? T minus 2. Okay, so I will swap the signs because of this. E to the minus 0.5 t minus 2, t minus 2, minus e to the minus 0.5 t. Okay, right? So I can write this guy as e to the minus 0.5 t times e to the 1, right? E to the 1, which is e, minus e to the minus 0.5 t. So essentially I will have e to the minus 0.5 t, e minus 1. This is the expression for this third part of the curve. Okay, this part here, and this regime will last forever. It will asymptotically approach 0 here, right? So what's the expression again? E to the minus 0.5 t. So here it's e to the minus 0.5 t multiplying e minus 1. E minus 1. Okay, and here it's 0. So in this case, we have three different regimes. The regime with negative time, the regime where t is between 0 and 2, and then finally the regime where t is larger than 2. So I just wanted to do this to show that here for continuous convolution, we can also describe the convolution as a weighted sum of past samples. So here I'm always integrating from t minus 2 to t. So it's the same thing that maybe it's easier, it's more intuitive for discrete convolution, but it also works here with continuous convolution. Okay. So there's an activity here. Let's check it really quickly. What do you have to do in this activity? You just have to do an animation for this convolution where both signals are the same rectangle. You can use the code that I used to generate these animations. So it might be easy. Let's check my code. So script. If you choose to use my code, it's just a matter of defining x of t and h of t in the form of functions here, and everything should work perfectly fine. And then you will do the same again, but this time the duration of the rectangles is different. This one has duration 2, this one has duration 3. So I want to show you what will happen in each case. Please notice that here the result will have a duration of 4, which is 2 plus 2, and here it will have a duration of 5, which is 2 plus 3. Okay, that's it for the continuous time convolution, and very soon I will post the video about continuous time frequency response. Okay.